Welcome to today's session on DC-DC converters. We are going to take a look at the buck converter, and before we do that, we want to take a very quick look at a very basic switching converter. The main purpose is to reduce an input voltage which is high enough, which is high than what is required for a given load or for the load that we are interested in. That is the basic switching converter, where we have an input source Vs, we have a diode, we have a transistor here which we are using as our switch, and we have a load RL, and the voltage across our load is VO. A simplified form of this diagram is seen over here, where the transistor has been replaced with a switch. And the way this operates is you are going to run this at a certain period, and within that period you are going to be turning the switch on and off to try to average out the voltage that you are interested in. So if you are operating at a given period and you turn the switch exactly 50% on and off, then what it means is that the voltage Vs is going to be split up into two. So if you have 5 volts, then you are going to have exactly 2.5 volts across the load if you switch it exactly half the period. So it comes on exactly 50% of the period and it goes off the other 50%. So we can use basically the switching on and off to adjust the voltage across our load. In a nutshell, that's what we are showing over here. So in this graph that we have, if I grab my pen very quickly, in this graph that we have, when the switch is closed, we have the voltage Vs across our load, and when the switch is open, then there is no current flowing, which means the voltage across our load is 0. What that implies? This implies that within one period we have part of the input voltage across our load, and then the other part of the period the voltage is 0. How do you calculate the average voltage? When we go back to first principle, so let's go up slightly here. So from first principle, if we want to find the average quantity, so that is the output voltage VO, and the average expression that we need to use is over here. We know that from 0 to t, it's only the period which is from 0 to dt that the signal is going to be on. What is D? D is basically known as the duty ratio. That is the ratio of the period when the switch is closed to the whole period that you have. So D is basically our duty ratio. When you do this integration, you are going to come out with an output expression which is given by that. This says that our output voltage, the average or the DC voltage across the load, is given by the duty ratio multiplied by the input voltage, which is Vs. This is basically the expression for the basic switching converter. You are going to see that if our duty ratio happens to be 0.5, which is half, then we are going to obtain exactly half of the input voltage always across our load. So based on the input voltage that we need, it means we can vary D accordingly to obtain what we want. Down over here is a basic expression for the duty ratio, which is basically telling you that the expression is the time period when it is on over the sum of the time period when it is on plus when it is off, which is basically the period of the waveform. So this is the expression for a basic switching converter. This is the expression we want to obtain, and this is what we want to have in a very simple converter. So let's go and take a look at our buck converter. So that is the buck converter we have over here. That is the circuit for the buck converter. We want an output voltage that is purely DC. We want an output voltage that is purely DC. So that is one main difference from the buck converter compared to the basic switching converter, where although your average voltage is what you required, the output is not continuous, so it's on for some time and it is off for some time. In the back converter, we want to obtain, if I grab my pen very quickly, in the back converter we want to obtain an output voltage which is purely constant. We do not want an output voltage in a back converter. Let's go ahead and delete this. We do not want an output voltage in a back converter which looks like that. Now, although the average of it is what we want, we don't want this waveform across our load. So that is basically what we want to use the back converter to achieve. How do we do that? So here is the circuit for the back converter. We have an input voltage. We have a diode which is going to help circulate the current in the inductor when the switch is open. We have a capacitor which is mainly used for filtering, and then we have our load. We are going to go through this circuit more in a more detail when we start doing the analysis for it. So for now, let's go up. Let's move up slightly. A very brief description of what a diode does. It basically provides a path, as stated over here, for the inductor current when the switch is open. So that is the main purpose of the diode that we have. When the switch is closed and we have current flowing, so when this switch is closed and we have current flowing from the source through to the inductor, the diode becomes reverse biased. The diode becomes reverse biased. Therefore, it becomes an open circuit. So the diode is open in the first period when the switch is closed, and then the diode becomes a closed circuit when the switch is open to provide a path for the inductor current. The voltage current relationship. So the input voltage to the filter is going to be Vs when the switch is closed. So when we close this switch, basically this is the filter side of the circuit. If I want to show you this very quickly, so that is basically the filter side of the back converter. So that is, this part here is a switching part and this is a filter part. So the input voltage to the filter side of the back converter is equal to Vs when the switch is closed. Don't forget the diode becomes an open circuit when the switch is closed. Let's go ahead and erase that. And let's go down. And the input voltage to the filter is going to be 0 when the switch is open. And everybody sees that very clearly, because when we open this switch, the diode stands on to provide a path for the inductor, and if this diode is assumed to be an ideal switch, then basically the turn on voltage is going to be 0. Therefore, when it is conducting, the voltage Vx, which is basically the voltage to our filter, is going to be 0. So that is what we have over here, and we are making the assumption that this circuit is being switched on and off at a D2 ratio of V. Some assumptions we want to make going along. The diode is going to remain forward biased for the entire time when the switch is open. So that's the first assumption we want to make. The second assumption also is that the inductor current is going to remain positive all along. So the inductor current is going to increase during one of the cycle and is going to start decreasing during the other part of the cycle, but then is going to remain positive. What do I mean by that? If I grab my pen, and this is basically what is known as continuous mode of operation. So this is what we mean. We want the inductor current when everything is operating in steady state. When everything is operating in steady state, we want our inductor current to be positive. Okay, this writing is giving me some headache here right now. Let's go ahead and erase this one, and then we draw it again. So we want the inductor current to be positive during the operation, and this is what is known as the continuous current mode of operation. In the text, you are going to see this as CCM. Let's reduce this size back. So in the text, you are going to see this as CCM, basically meaning continuous current mode of operation. So that is what we want when this buck converter is operating normally. When the inductor current goes to 0 during one complete period, that mode of operation is known as a discontinuous mode of operation. And we are going to take a look at this when we are done with the analysis later, to see the difference between the continuous current mode and the discontinuous current mode of operation. This lecture is going to be end here, and we are going to have another session which is going to pick up from here. Thank you.